Okay, here are two examples of rational functions. So you see in each of these, the numerator and the denominator are both polynomials. So in general, a rational function is a fraction where the numerator and denominator are polynomials. Okay, let's look at the graphs of a couple of rational functions. Okay, so what you notice here is that there are a couple of x values in which the function is growing, 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 and falling, falling, falling without bound. So falling without bound and growing without bound. These guys here are called vertical asymptotes. Okay, this arrow here indicates that the function is getting closer and closer and closer to the x-axis in this direction. And this is indicating that the function is getting closer and closer and closer to the x-axis in this direction. When you have a horizontal line where that happens, namely the graph is getting closer and closer and closer to it, those are called horizontal asymptotes. So in this case, the x-axis is a horizontal asymptote. Okay, let's take a look at this function. So we see here that we have a vertical asymptote because the function is getting closer to it. So this guy is a vertical asymptote. We also have a horizontal asymptote here because the function is getting closer and closer and closer to that horizontal line at y equals 2. Okay, let's see an example where we find a vertical asymptote. The first thing that we need to do is make sure that the numerator and denominator don't have any common factors. These are both linear terms, and they don't have any common factors. The next thing that we need to do is find out where the denominator equals 0, okay, once we've canceled out any common factors. In this case, the denominator is equal to 0 at -1/2. Okay, so that means that the line x equals -1/2 is a vertical asymptote of this function. Okay, let's recap the process of finding a vertical asymptote. Okay, so first we need to cancel any common factors between the numerator and the denominator. Then we find the zeros of the new denominator, and those are the x-coordinates of the vertical asymptotes. Okay, try this one. Okay, press pause while you work on it. Okay, so you should have found that the numerator factors as x plus 2 times x plus 1, and the denominator factors as x minus 5 times x plus 1. So we cancel the two x plus 1's, and we're left with x plus 2 over x minus 5. The value of x that makes our new denominator equal to 0 is the x-coordinate of the vertical asymptote. Okay, so x equals 5 is the vertical asymptote. Okay, now let's talk about horizontal asymptotes. Those are a bit more involved. Okay, let's take a look at this one here. Since the degree of the numerator is 2 and the degree of the denominator is 2, the horizontal asymptote is the ratio of the leading coefficients. Okay, so that is, the horizontal asymptote is y equals 3/5. In this case here, the degree of the numerator is 1, the degree of the denominator is 3. When the degree of the denominator is larger than the degree of the numerator, then y equals 0 is a horizontal asymptote. Okay, finally the last case that we have is when the degree of the numerator, which in this case is 5, is larger than the degree of the denominator, which in this case is 3. When that happens, there is no horizontal asymptote. Let me summarize these observations for you. Okay, so if the degree of the top and the bottom is the same, then the line that goes through the ratio of the leading coefficients is the horizontal asymptote. Just like in this case here, the degree is the same, y equals 3 divided by 5 is the horizontal asymptote. If the degree of the numerator is larger than the degree of the denominator, there is no horizontal asymptote. That was like this case. The degree of the numerator is larger than the degree of the denominator. Finally, if the degree of the top is smaller than the degree of the bottom, the line y equals 0 is a horizontal asymptote. That was like this case. The degree of the top is smaller than the degree of the bottom, so y equals 0 is a horizontal asymptote. Okay, let me give you some to try. Press pause now. Okay, in the first case, y equals 0 is a horizontal asymptote because the degree of the top is smaller than the degree of the bottom. In the second case, it's y equals 8/5 because the degree is the same, so the horizontal asymptote is the ratio of the leading coefficients. Finally, in the last case, there is no horizontal asymptote because the degree of the numerator is greater than the degree of the denominator. Okay, let's examine the second case in a little more detail. Okay, when we're looking for horizontal asymptotes, we're really actually examining the end behavior of a function. Remember, for the end behavior of the function, we're looking at what happens as x goes to infinity and as x goes to negative infinity. So that means that x is really, really large in magnitude. If you look at the numerator here, this x to the fifth really overpowers these lower order terms for such large values of x. So these guys become insignificant in the grand scheme of the end behavior. Likewise, in the denominator, the x to the fifth really overpowers these lower order terms, so they become insignificant in the end behavior of the function. So the end behavior of this function is really governed by 8x to the fifth divided by 5x to the fifth. And this, you see, simplifies to 8 divided by 5. So that's why y equals 8/5 is the horizontal asymptote, because these guys become insignificant for large values of x. So the overall function reduces to just y equals 8/5. Okay, now let's talk about the domain of a rational function. The domain of a rational function is fairly easy to find. It's just the values of x, except those that make the denominator equal to 0. So, for example, if we have f of x equals x squared plus 10x plus 1 divided by x squared minus 8x minus 20. To find the domain of this guy, we just need to find out what makes the denominator equal to 0. Okay, so this denominator factors as x minus 10 times x plus 2. 10 makes this one equal to 0, and negative 2 makes this one equal to 0. So x cannot be equal to 10, and it cannot be equal to negative 2. So the domain of this is all reals, or all real numbers, except 10 and negative 2. Okay, try this one. Okay, you should have gotten all real numbers except 2 and negative 2, because this denominator here factors as x plus 2 times x minus 2. And x plus 2 times x minus 2 is equal to 0 if x is equal to negative 2 or 2. So the domain of this guy here is is all real numbers except 2 and negative 2. If we want, we can use some fancy notation. We can write the set of all x such that x is a real number and x is not equal to 2 or negative 2. Okay, again, this right here means that x is a real number and x cannot be equal to 2 or negative 2. That would be the fancy way of writing this statement.